Hello students, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we're working through the brand new June 2026 New York State Chemistry Regents, cluster by cluster. This is the 9th video in the series where we're going to tackle the photosynthetic pathways cluster. If you're looking for a different cluster, check out the playlist linked in the description below, which has all of the 11 clusters linked. Let's get started. All right, so as with all the clusters, we're going to start with reading the passage for understanding. So here we go. In 1957, an experiment was performed to determine the source of oxygen atoms in the glucose molecules produced during photosynthesis. Oxygen 18, a stable isotope of oxygen, was used to produce enriched water containing 100 times more of this isotope than normal. This allowed the oxygen 18 to be traced in the photosynthetic process. Algae were allowed to photosynthesize for 20 minutes in the enriched water. Next, the algae were transferred to non-enriched water where they continued to photosynthesize. Since O18 cannot be directly detected, the following sequence of steps was used to detect the presence of O18. The first step, the O18 underwent a nuclear transformation to become unstable F18. The unstable F18 emitted a particle and decayed to oxygen 18. And the particle emitted by the F18 was detected and used to determine the presence of oxygen 18. The results of the experiment demonstrated that none of the oxygen 18 from the enriched water was found to be in the algae. Figure 1 represents photosynthesis occurring in algae in enriched water. All right, so then we have the passage, and then we have the diagram, and then question 38. Asks to identify the missing component labeled X and write the coefficient to balance the equation. Hopefully, we don't really need to use too much of the information from the passage to answer this question, and you can recognize that this is just a simple photosynthesis question. So if you know that photosynthesis requires H2O, water, and carbon dioxide, CO2, you can deduce that this is what must be forming the glucose right here, and then the oxygen. So maybe you memorize how to balance this, but at the very least, hopefully recognize that it's CO2. From here, let's assume that we don't know how to balance. I noticed that I have 6 carbons on this side, which means that I also need to have 6 carbons on that side. We would then need to check that the oxygen adds up. So let's do that. So counting the oxygens in the H2O, here I have 6 oxygens, and then 6 times 2 in the CO2 would give me 12 oxygens, for a total of 18 oxygens on this side. If we count that up over on the product side, we can see that within the C6H12O6, I have 6 oxygens, and within the 6O2, 6 times 2 is going to be 12 oxygens, for a total of 18 oxygens. So that's going to balance out, and that is your correct answer. All right, the next question, 39. Identify the particle that allows scientists to confirm the presence of oxygen 18. So for this question, we're going to have to go back to the passage. If we look over the passage, it's talking about a nuclear reaction happening, and then in this bullet point here, it's saying that the oxygen 18 underwent a nuclear transformation to become unstable F18. So there is a particle that's emitted as we are taking F18 and decaying it to oxygen 18. Right? This is noted in the second bullet point. And then it's saying that the particle emitted by the F18 was detected and used to confirm the presence of oxygen 18, right? And then this question is just asking us, what is the particle? So we've got to write a nuclear equation here. From the second bullet point, we know that we're starting with F18. So I'm going to say 18 fluorine. And then that's going to decay into 18 oxygen. Now, if we wanted to get the bottom numbers, which I think is relevant, those are your atomic numbers. You can go to your periodic table. Don't mind my notes here from the last video. And we can see that an 8 corresponds with oxygen and a 9 corresponds with fluorine. So let's go ahead and fill that in. And then we want to begin to think about what particle was released. Well, if we look at this equation, we notice that the mass does not change. However, the atomic number is going down by 1. Okay, maybe you recall from class that the conversion of a proton into a neutron is beta decay. Essentially what you're doing is you're just losing the positive charge, or I'm sorry, not beta decay, is a positron decay. So maybe what you recognize is you're just losing the positive charge through positron decay. So you're losing a positron. Now what you need to do is figure out what is the symbol for the positron. So we can go and look at our nuclear notations right here. And we can represent the positron as either +1e or +1b. I like to use the b. So that's the particle that we're looking for. We're looking for a positron. All right, moving along. Magnesium ions are essential for plants to perform photosynthesis. Aqueous magnesium ions are absorbed from the soil through the roots. Soil pH also affects magnesium absorption. Magnesium absorption is reduced by half in soils with a pH of 4.5 compared to soils with a pH of 6.5. The pH of soil is essential for crop production and affects plant health. Raspberries grown in New York State benefit from a soil pH of 5.5 to 6.5 for optimal growth. The soil in the northern Finger Lakes region of New York State has a pH of above 7. Elemental sulfur, aluminum sulfate, and manure can be used to lower the pH of soil. Limestone and dolomite can be added to acidic soils to increase the pH of soil. There's a lot of information there that we're going to have to refer to for the next two questions. But question 40 says, which claim identifies how hydronium ion concentration in soil with a pH of 6.5 compares to soil in which the magnesium absorption levels are reduced by half? First thing I want to do is figure out what is the pH of the soil with magnesium absorption levels that are reduced by half. If we go to the passage, it states that magnesium absorption is reduced by half in soils with a pH of 4.5 compared to soils with a pH of 6.5. All right, so the pH of these magnesium absorption levels that are reduced by half is going to be pH 4.5. The question is asking us to compare hydronium ion concentrations in that soil with 6.5 to 4.5. We need a little bit of acid-base chemistry here. So what we need to know is that when we change the pH by 1, we're going to change the H3O plus, the hydronium ion concentration, and the OH minus ion concentration by 10 times. All right. If we're going to change the pH from 6.5 to 4.5, this is a 2 times decrease in pH. All right, that means that the ion concentration is going to change by 10 times 10. Thus, it's changing by 100 times. Okay, now we have to think, is this 100 times concentration either increasing or decreasing? In the case of this soil, if we're going from pH 6.5 to 4.5, we have a 100 times increase in H3O plus. We have a 100 times decrease in OH minus. All right, so let's take a look at the answer choices. This says the hydronium ion concentration is 100 times more compared to the soil with reduced magnesium levels. Right? This is another way that they trick you in the wording. All right, so this is saying that the hydronium ion concentration is 100 times more in the soil with pH 6.5 than the soil with reduced magnesium levels, that's pH 4.5. The hydronium ion concentration is 100 times more in this soil, right, with pH 4.5. But the question here, or the answer choice here, is saying that you have 100 times more in the soil with pH 6.5. That's not true. We have 100 times less H3O plus and 100 times more hydroxide. Answer choice 2 is saying that the hydronium ion concentration is 100 times less compared to the soil with reduced magnesium levels. This checks out, right? Because in pH 6.5 soil, you do have 100 times less H3O plus than in pH 4.5. So this is the correct answer. Choices 3 and 4 are implying that the hydronium ion concentration is 2 times either more or less, but the pH change is 2 times. The concentration is going to be 10 times 10, which is 100. So we can eliminate choices 3 and 4. All right, question 41 says a farmer in the northern Finger Lakes region of New York State wants to grow raspberries. How would a commercial manufacturer of soil additive make a product to maximize its short-term and long-term effects on raspberry growth? So there's some information that we need to know. Right? We need to know what the pH of the soil is in the Finger Lakes region, and we need to know what the optimal raspberry growth is, or what the optimal pH for raspberry growth is. So let's go to the passage and underline the information that we need to know. So right in the passage, we can look, and it says that raspberries grown in New York State benefit from a soil pH of 5.5 to 6.5 for optimal growth. And then it says that the soil in the northern Finger Lakes region of New York State has a pH of above 7. So part 1 here, we know that our soil pH is 7. And then part 2 is we need to lower the pH to 5.5 to 6.5. All right, so in order to lower the pH, we need to assess how dolomite will react with the soil and how aluminum sulfate will react with the soil. So let's go back to the passage to figure that out. It says that elemental sulfur and aluminum sulfate and manure can be used to lower the pH of the soil. And limestone and dolomite can be added to acidic soils to increase the pH. So dolomite is going to increase the pH. So we can eliminate choices 1 and 2 because we want to lower the pH. And this is implying that you put dolomite in. Then, we know that we need to use aluminum sulfate to eliminate or to lower the pH. So now we have to think about crystal size. If we have small size crystals, this means that we have a very high surface area. Hopefully you remember from your kinetics unit that increasing the surface area of something is going to cause a very quick reaction. So if we use very small size crystals, this is going to result in a very drastic drop in pH, and then all of the aluminum sulfate is going to dissolve into the soil, and that's really going to be that. If we use different size crystals, like we do want to drastically lower the pH at first because we want to get the soil optimal for raspberry growth, but we also want to focus on short-term and long-term effects. So in the short term, the small crystals can lower that pH quickly. And for long term, larger crystals will stay in the soil more, and then they will continue to lower the pH as needed. All right, so the best answer choice here is going to be 4 in order to maximize those short-term and long-term effects. So that's it for this cluster. If you found this helpful, please be sure to like the video and subscribe for more Chemistry Regents walkthroughs. When you're ready, you can go to the description and find the playlist for the other 11 clusters. Happy studying!